Jai Hind friends, myself Dr. Pankaj Goel, Assistant Professor in EC Department at AKGEC Engineering College. Today we will discuss a very important topic of ion implantation. It is from the subject VLSI technology. The contents of our presentation is introduction, diffusion versus ion implantation schematic and working principle, range theory, stopping mechanisms, damage and annealing, channeling, shadowing, and reference. So, ion implantation is a low temperature technique for the introduction of impurities into the semiconductor wafer. And ion implantation offer more controlled doping than diffusion process. In diffusion, we know that the surface concentration is always going to be the highest concentration, and because in case of diffusion it is a high temperature process, the diffusion of dopants happen from higher concentration region to lower concentration region. But in case of ion implantation, because it is a low temperature process and it is not a diffusion process, so it is not always the case that the surface concentration is always the highest. Let us compare the diffusion and ion implantation process with the help of this figure here. As we can see, there is an area where dopants are to be inserted into the wafer. There is an opening there, and if you compare the doping that happened in diffusion and ion implantation, you will see that in case of ion implantation it is more controlled doping. Dopants are introduced vertically. Whereas in case of diffusion, when we have introduced the dopants through this opening, in addition to the dopants diffusion happening vertically, it is also happening laterally. So lateral diffusion is also happening. So ion implantation is more controlled doping process. Now, this is the schematic of a ion implantation machine. Here the main components, main sections of this machine is ion source that we have here. We have a ion analyzer magnet, ion beam, ion selection aperture, acceleration tube, lens, Y and X scan plates, wafer, and the rotating mechanism that is used to rotate the wafers. So this is the schematic of a ion implantation machine. Now, in case of ion implantation, what we do is the dopants that are to be introduced into the wafer, they are ionized, accelerated, and directed at a silicon substrate. When they are directed towards a substrate and when they collide with the silicon atoms there, they gradually lose their energy and finally comes to rest at certain depth within the lattice. Now, the depth that they can penetrate in the wafer can be controlled by providing a acceleration energy of particular amount, and the dopant dose can also be controlled by monitoring the ion current during the implantation. So in case of an ion implantation system, the basic requirement is to provide a beam of ions of a particular type and energy to the surface of the silicon wafer. And in case of ion implantation, generally the dopant source is a compound of a dopant material. It is a compound material and usually a gaseous compound. Okay, and what happens is there is a high voltage enclosure section in the ion implantation machine, which consists of a gas source and an ion source. A gas source is a dopant compound gas such as BF3, and there is an ion source which consists of heated filament which cause the molecules to break up into the fragments. An extraction voltage of around 20 kilovolt cause the charged ion to come out of the ion source and enter into the analyzer. The next section after the high voltage enclosure section is analyzer section. We can see here, this is our analyzer section. This is our ion source. Okay, the dopant ions from here comes to the analyzer section. Now, the magnetic field of the analyzer is chosen such that only the ions with the desired charge to mass ratio can travel through it without being blocked by the analyzer walls. Because we have to allow only the desired ions to pass through it and enter the wafer. Because when we are generating the dopant ions in the high voltage enclosure, there may be some contaminations. And those contaminations are undesired and they are not allowed to go to the wafer. So, to pass only the desired dopant ions to the wafer, we are using this analyzer mechanism, which consists of a magnetic field. And the magnetic field of this analyzer is such that only the desired dopants of a particular charge to mass ratio can travel through it. All others are blocked by the analyzer walls. So, a charged particle of mass m moves with velocity v, and this is the characteristic of a particular dopant. Now, the dopant ions which pass through this analyzer, they continue to the acceleration tube, that is our next section. The acceleration tube, that is our next section. The dopant ions which pass through analyzer, then they go to the acceleration tube, where they are accelerated to the implantation energy. Means the desired energy that is required for dopants to penetrate a particular depth in a wafer, that energy is provided in the acceleration tube. And apertures, we use apertures also. Apertures are used to ensure that the beam is well collimated. We can see here the beam with the help of the aperture is well collimated, straight lines. Okay. Then we can see here we are also using a electrostatic deflection plate mechanism. Electrostatic deflection plate mechanism. This method is used for aligning the path of charged particle. Aligning the path of charged particle by applying the electrostatic field between the deflecting plates. A commercial ion implantation system is typically 6 meter long, 3 meter wide 2 meter high and consume around 45 kilowatt of power and can process 200 wafers per hour with the specification of those 10 raised to the power 15 ions per square centimeter and 100 mm wafer. So this is a ion implantation schematic and the principle of working. The next topic is about range theory. Now, range of ion is the distance traveled by the dopant ions during which the ion energy has fallen from its initial energy to zero value. Means when the ion energy becomes zero, that is the point when the ion come to rest, and that is the point up to which the dopant ions have penetrated into the semiconductor. Now, as the dopant ions are bombarded onto the wafer surface, finally they come to rest. Now, how they are stopped inside the wafer? For that there are two mechanisms. One is the nuclear stopping and the other one is electronic stopping. The first one is nuclear stopping and the second one is electronic stopping. In case of nuclear stopping, what happens is the dopant ions collide with the nuclei of the silicon atoms, wafer atoms, and in the process they lose their energy, they displace the silicon atoms. That is the nuclear stopping, where the dopant ions collide to the nuclei of the silicon atoms and displace them from their position, and it causes a lot of damage in the wafer. Second one is electronic stopping. In electronic stopping, the dopant ions do not collide head-on with the host silicon wafers, but they lose their energy to the bound electrons of the host silicon atoms. They keep on losing their energy to the bound electrons, and in the process those bound electrons become free and they break the covalent bond and become free charge carrier. So that is electronic stopping mechanism, and in this mechanism the wafer is not damaged. Now if we see here graphically, we can see in the first figure, this is the nuclear stopping mechanism in which the dopant ions collide with the silicon atom and both get displaced from their position, and it causes the damage in the silicon wafer. The second mechanism, as we can see here, the dopant ion is not colliding with the silicon atom head on, it is actually losing its energy to the bound electrons, and in the process the bound electron become free by breaking its covalent bond, and the dopant ion lose some of its energy in the process. So if the electronic stopping mechanism is occurring, in this deep penetration happens. Deep penetration of the dopant ions happens. So nuclear stopping and electronic stopping, they are the two stopping mechanism in ion implantation. Now here we can see the comparison between ion velocity and the stopping mechanism. Here we can see, like, if the ion velocity is low, that is the energy of the ion, dopant ion is less, then primarily it is the nuclear stopping. If the energy is intermediate or high, then electronic stopping mechanism plays a significant role. Means out of total energy, how much energy is lost by nuclear stopping mechanism and how much energy is lost by electronic stopping mechanism, that is shown here. In case of low energies, it is more of a nuclear stopping, and in case of intermediate and higher energy is more of electronic stopping. Also, if the ions are lighter, then it is more electronic stopping, and if there are heavy ions, then it is more nuclear stopping. Like boron is a lighter ion, so electronic stopping mechanism plays a more important role here, and arsenic is a heavier ion. In this case, nuclear stopping plays an important role. As we know that, just we have discussed that when the dopant ions collide with the host silicon atoms, they damage the structure. Now, we can see here the wafer structure before implantation and after implantation. Here we can see that after implantation, the structure is damaged. It is not a regular structure. All the atoms are displaced from their regular positions. So this may also be known as amorphous structure. Amorphous structure. Now, this damage of silicon wafer need to be healed. We cannot leave it as it is, because if the silicon wafer is not in crystalline form, it is in amorphous or damaged form, it cannot be productively used for electronic circuitry. Okay, so this is what we have just discussed, that there is a series of nuclear collisions due to which the damage happens. Okay, and binding energy of a latticite is only 10 to 20 electron volts, so it is very easy to transfer enough energy to free an atom from its position. And this displaced atom can also travel and collide with other silicon atoms. So the energy is spread over many particles. So the result of one incident ion has been the displacement of many target atoms through nuclear scattering. So means one dopant ion is capable of displacing many silicon atoms from their regular positions through nuclear scattering. Now, these damaged structure need to be healed, need to be reordered in the crystalline form, and this is done with the help of annealing process. This is a very important process, annealing process, which is used to repair the damage caused by ion implantation process. Now, let us see here. Annealing is a heat treatment process used to restore the disordered semiconductor wafers to single crystal structure. And the success of annealing is often measured in terms of fraction of dopant that is electrically active. It is not the case that the dopant atoms that we have introduced into the wafer, all of them are electrically active. Until and unless they do not come to the substitutional sites and make a proper covalent bond with the host silicon atoms in its surrounding, they are not electrically active and they are not functional. So when we introduce the dopant ions, the structure is damaged. Most of the dopant ions are electrically inactive. Now, when we do the annealing process to make the wafer structure into the regular silicon single crystal form, these dopant ions become electrically active, and that is the measure of success of annealing. That is how successful the annealing is. it depends on how many dopants are electrically active out of total dopants. So in annealing, the main challenge is not only to repair the damage and activate the dopants. In addition to it, there is one more important challenge, and that is that diffusion should not happen. We know that diffusion is a high temperature process, and when we do the diffusion, when we do the annealing, because annealing is a high temperature process, and when we are raising the temperature of the wafer, diffusion will automatically happen. And diffusion means the dopant ions will go to those areas in a wafer where we don't want them to go, because we have already done the ion implantation. We have already penetrated the dopants into the desired areas, and at high temperature, when annealing is going on, dopant ions from those areas, from those desired areas in wafer, they are moving to other areas, which is undesirable. And that is the main challenge, that annealing, while repairing the structure and making the dopant ions electrically active, the diffusion should be minimum. And to do so, to achieve that, we can use rapid thermal annealing. Means we are not doing annealing process for a long hours. We are only doing it for few seconds. It's of the order of seconds, so that the structure is damaged, the damaged structure can be repaired, and the dopant ions become electrically active, and at the same time, much diffusion is not happening. So as we do the annealing, we can see that the structure is becoming ordered. As we can see, the structure is becoming more and more ordered. We can see. Now, another very important topic related to ion implantation is channeling. As we know that in ion implantation, high energy dopant ions are bombarded on the wafer, and depending on the angle of bombardment or direction, it may happen that certain dopant ions do not encounter any silicon atoms in its path, and they just travel through the complete wafer, as we can see here. Here we have taken two conditions, one in which there is a lot of collision. If our dopant ions are coming in this direction, then this dopant ion is encountered with various silicon atoms. Whereas if we are entering our dopant ions through this angle, then we can see there is no collision. There is no host silicon atom in its path. So this is known as channeling, and it is of course undesirable, because our doping profile will change due to channeling effect. Another figure, please see. This is our dopant ion, which we name it channeling ion. Channeling means because it is not encountering any silicon atom in its path, and it has traveled to the end of the wafer without encountering any silicon atom. Another is collisional ion. Collisional ion, in which it is a bit tilted, and when it is entered by this angle theta into the wafer, it is encountering the silicon atoms to which it is colliding. So it depends on the angle also means it whether our dopant ion will encounter some host silicon atom in its path or not. Okay, so we can see here, if the dose is much smaller and the ion beam is directed along a major crystallographic axis, that is 110, then the disorder is less. Whereas if the dose is increased, the amount of channeling become less. Higher the dose is, more the disorder. Okay, if we increase the dose, it will lead to more nuclear stopping, more disorder, more amorphous structure. So channeling effect will be minimum in that case. Now this is an example of a post collision channeling. Means it may also happen that initially our dopant ion has collided with one of the host atom or few of the host atom, and after that it has taken a path in which it is not encountering any silicon atom. So here we can see in this first section, our dopant ion is colliding with the silicon atoms. We can see here, first it is colliding with this silicon atom, then it is colliding with this silicon atom, and like this, then with this, and then with this. But when it is entering into this region, second part, it has taken a angle in which it is not encountering any other silicon atom in its path. So it has traveled a long path. And then it may have encountered, in the third section, it has encountered a silicon atom, and then finally after collision it stops. So the point here is that it is not necessary that channeling ion does not collide with any host ion at all. It may happen that initially it collide with some of the silicon atoms, and then it take an angle such a way that further it go deep into the wafer without collision. This is the shape of the post collision channeling shown here. Now this one is about lattice damage with one ion. We have taken an example of a lighter ion and heavier ion. In lighter ion case, we can see that it cause damage to a greater depth because a lighter ion can travel longer, whereas a heavier ion cause damage in a shorter length, shorter depth in a wafer, but the damage that it cause is in a it cause maximum damage in small region. The outcome of this is maximum damage in small region, whereas a lighter ion which can travel to a longer distance, it cause long narrow damage. Okay. Next topic is shadowing effect. As we discussed that it may happen that the dopant ions beam that is bombarded on the wafer is not straight with a straight angle. It may have some tilted angle, and if there is a tilt, then what impact it may have on a wafer doping, that is known as shadowing effect. Like in this case, we can see that the ion beam is entering in the wafer with a certain angle. Okay, so what will happen is this is our doped region. Okay, this is our doped region. Now, in this, after the ion implantation, there is a area in which there is no doping. There are no dopants because the ions were coming at a certain angle. So this area is left. There is no doping here in this section. In this section, there is no doping. So that is shadowing effect, and it can be healed with the help of a annealing process. Here, annealing is we know that annealing is a high temperature process in which dopants from higher concentration region travel to lower concentration region. So the dopants from this higher concentration region, go to low concentration region in the left direction. So shadowing effect problem can be overcome by annealing and diffusion. Now, there are certain important questions of this topic that we discussed that have been asked in previous examinations. Kindly have a look over it. What is meant by annealing? Explain ion implantation process, its advantages and drawbacks. What is ion implantation? Why is ion implantation preferred over diffusion? And explain briefly the ion implantation technique with labeled sketch. Again, the question has been asked in a different way. Explain ion implantation technique with labeled sketch. Also mention its advantages and disadvantages. So these are certain important questions from this topic. The book that we are referred for this presentation is SMZ, VLSI technology from McGraw-Hill edition, McGraw-Hill Education. Thank you.